All right, please let's look up. We'll be looking at optical activity in monosaccharides. Optical activity in monosaccharides. Now, for a substance to be considered optically active, that compound must be able to rotate what? Plane polarized light, a beam of plane polarized light. Now, in monosaccharides, due to the presence of chiral carbon, we've seen that chiral carbon have 4 different substituents, right? The presence of chiral carbon in monosaccharide is what is responsible for the optical activity of monosaccharides. Are we together? Now, if the monosaccharide rotates light to the right, we call it what? Dextrorotatory. And it can be designated as plus or D. So dextrorotatory, it rotates light to where? The right. Level rotatory rotates light to the what? Left. And can be designated as what? Minus or what? Or L. Minus or L. Alright. Now, apart from so we've seen that dextrorotatory, they rotate light to where? Right, while level rotatory rotates light to left. Now, a pair of optically active compounds that are mirror images of themselves is called what? Enantiomers. So enantiomers, if you have a pair of optically active compounds, like take for example, if you have something like this, now if you have something like this is the structure of what? Glyceraldehyde, right? But here, is this D-glyceraldehyde or L-glyceraldehyde? This is what? Remember, when you want to assign, the reference carbon is always the penultimate carbon, the second to the last carbon. So if it is on the right, we designate this what? D, right? Or plus. So this is D-glyceraldehyde. Now, if you look at this is L, right? So this is L-glyceraldehyde. Is this optically active? It rotates light, right? So it is optically active. Now it rotates light to the right, right? So we said it is dextrorotatory. This one is optically active. It rotates light to the left. So we said it is what? Level rotatory. Now if we mix this one, if you notice this one is a mirror image of this one, right? If you keep a mirror like this is a mirror image of this. So a mixture of two optically active compounds that are mirror images of themselves. If you mix this one and this one that are both optically active and mirror images of themselves, we call that what? Enantiomers. So example of enantiomers, we have D-glyceraldehyde and L-glyceraldehyde. We also have D-glucose and what? L-glucose. Why? They are both optically active and they are what? Mirror images. But if we have a pair of optically active compounds that are not mirror images of themselves, we call that what? Diastereoisomers or diasteriomers. So if the optical isomers you are mixing are mirror images, you call that what? Enantiomers. If the optical isomers you are mixing are not mirror images, you call that what? Diastereomers. Take for example, if you have a mixture of galactose and mannose, if you draw the structure of mannose, This is the structure of mannose. And if we draw the structure of galactose, now this is galactose. If you look at this, is this optically active? Is mannose optically active? It's optically active. Why? Because that's chiral carbons, right? Good. Will you designate this D or L? D or L? This is D, right? I told you anytime you want to designate either D or L, check the second to the last carbon. If the OH is on your right, you call it D. If it is on your left, you call it what? Is this optically active? It's optically active, right? Because we have chiral carbons. Is this D or L? D or L? D or L? D, right? Because the second to the last carbon, the OH is on your right. So this is still D. Good. Now, are these two things mirror images of themselves? If you look at this carbon here, this mirror image, right? This first one. This second one, is a mirror image? On the same side, right? So you see, this compound is not a mirror image of this compound. Do we get? Now, when you have a mixture of two optically active compounds that are not mirror images of themselves, you call that what? Diastereoisomers. But if the mixture of the stereoisomers are mirror images, you call that what? Enantiomers. Now let me ask, a mixture of two optically active compounds, will they be optically active or optically inactive? For example, if you have D glyceraldehyde and you have L glyceraldehyde, this one is rotating right to the what? Right? And this one is rotating right to the left. If you mix two of them, where will they rotate to? Where will the mixture rotate to? There will be no rotation, there will be no net rotation, because this one is rotating to the left, this one is rotating to the right? Now, a equimolar mixture of optically active compounds that are mirror images, that is, equimolar mixture of enantiomers, will give us what? A substance called what? Racemic mixture. Racemic mixture. Racemic mixture is equimolar mixtures of enantiomers. Now, are they optically active or optically inactive? Inactive, because the effect of this one, we cancel the effect of this one. One is rotating to the right and one is rotating to the left. So it will end up becoming optically inactive, racemic mixtures. So understand that if those two optically active compounds are mirror images of themselves, you call that what? Enantiomers, right? But if they are not mirror images, you call that what? Diasteriomers. Equimolar mixture of enantiomers will give us what? Racemic mixture. Any questions so far?